You guys should be in a window similar to mine as you just start up. In that window, you should see a tile that says 2-AP Calculus. Is anybody missing that tile? Your tablet's so slow. Lucia, you're missing it?
I'm trying.
You shouldn't be, because I have you listed as a member.
Oh, I see it. No, I see it.
You see it? Okay. I preloaded everybody in, so you should be there, but I have to do it manually, so every once in a while you miss a person or you end up entering, you type in the last name and you pick the brother, sister instead of the one you want, or, you know, like, stuff happens. All right. So you're going to set up your OneNote notebooks real easy. All we're going to do is click on the tile that says 2/AP Calc. From the side panel here, you're going to click on Class Notebook. It'll take a minute for that notebook to populate. Mine's coming in right now. Once this is dropped in, you're going to be using the drop down here. Mine says editing. I think yours will say viewing. From the drop down, you're just going to pick open in desktop. And then that'll load the new notebook for the semester in to your current OneNote. You can close first semester's notebook. I transferred all the notes from first semester in, so they're all the notes are there from first semester still, so there's no worries there. On occasion, you'll hit open in desktop and it won't be in your list here. If that's the case, if you just go to more notebooks, it should be listed in the stuff that you can open, and you just might have to open it manually. That occasionally will happen. I don't know why it happens sometimes and not others, but after you've done that, you're all set. You're in the new notebook for the semester, and we're ready to rock and roll. Okay. I'm going to talk for a minute while you guys finish up. If some of you guys said you had a slow tablet and you might still be kind of working through that process, I'm going to talk for a minute while everybody's getting caught up before we dive into new stuff. So our plan here at the start, we're going to be beginning semester 2 with the reverse process of differentiation. So the idea that we're going to start with is we're going to be starting with, okay, I have some derivative. How do I recover the original function from this? And then what are the applications of that process? And that's basically semester 2. Okay, so it's all the same topic of recovering the original function from the derivative, and how do I do that? And what does that allow me to do then afterwards? Like, what application can I use to do, or use that technique to do? For this first month or so, while we're doing that, there are, based on your semester exam, there are 2 topics from semester 1 that I would like to continue to do a little bit more practice on, and we'll have like a mini test, like a test score or a test grade for one topic. It won't be 100 point. It'll be like 25 point or something. But there's going to be 2 topics that I want to do that for, that based on the semester exam, I felt like they happened at the end of the semester and they were rushed, and I don't think we did a good enough job on it, and you guys weren't able to demonstrate much on your final. So I want to provide some more time and opportunity, incentive for us to get a little bit better at those 2 topics. Any guesses as what they are? Related rates and optimization. Yeah, you guys had probably a pretty good idea that was, when I said 2 topics from first semester that didn't go real well, I have a feeling you guys would have been able to guess those. So for the related rates piece, we're going to start there. And I have like, I think it's 4 sets of problems. I'm going to give you 1 set kind of each of the next 4 classes to work on, and we'll kind of go through it the next class. Just do a little bit more practice. I don't really want to do like a lot of additional instruction. On this, I'd rather have you guys work some problems and come in and we'll present some stuff and go through solutions and talk about like what to do and how to do it, and let you guys kind of make some corrections, and we'll talk about what you did or didn't know, or what you should have observed and not observed.
My computer won't let me open your window because it says my disk capacity.
Oh no.
Right? So that's what I think we should do.
Yeah, but let's do that like after class or whatever. Like, it's not. Yes.
Can I just have one more picture?
Oh yeah, did I not give you guys enough? That's what okay. Counting's hard sometimes, guys, you know? So, everybody feel okay with this part? We're okay with like spending a little bit of time here in the beginning, reviewing these couple of topics as we continue to plow forward into the new stuff. That's okay. As far as class setup goes, the class is set up in the same way that we did first semester. So we have, homeworks and homework quizzes and tests and all that jazz. Second semester, the homework quizzes are all going to be done. I should say almost all of them will be done through the MyAP. So I'm going to set up like multiple choice quizzes in there using their test bank of like questions. The idea will be that these questions will include recent stuff and first semester things. The AP exam is cumulative. I don't ever want to get like too far away from what we did in first semester. So I'm going to still kind of include first semester topics inside of these homework quizzes as review stuff. Now these homework quizzes will be like 5 to 8 questions. There'll be multiple choicers. We're going to time them because I want you to get used to the pace of the AP exam as well. So we're going to put like a time limit on it and give you something like, at the beginning it'll be like 3-ish minutes a question. We'll kind of like squeeze that down as we get a little bit more comfortable doing this stuff. Let you guys feel what the completion pace should feel like for an AP exam, just so you get a little bit more comfortable with that and familiar with that. We'll try to continue to do practice things like this to get ready more so in second semester than first, because that guy is, like coming at us quicker than you think. It's going to be AP exam time. Now, as far as scoring goes, these are multiple choice. They're going to be scored right and wrong. I'll have some kind of scale based on if you get, like 4 or 5 is like a 10. You get like, 3 is like a 9, like we'll have some kind of graduated scale. So like it's not, you don't have to get 100% of the questions right to get 100% on the homework quiz, because nobody expects you to get 100% on the AP exam, although like it'd be so fabulous. Like what a great feeling to get done and be like, yeah, I think I got them all right, and what to do for all of it. Like amazing feeling. Okay. Does everybody feel okay about like the short-term, long-term plan? The things that are going to be a little bit different than first semester, but not much, right? Just like changing the format a little bit to practice doing the multiple choice. And again, I think that the AP has changed their format so that, Marcelino, come on in. Change their format so that the multiple choice portion of the AP exam is done on the computer now. I'm not positive the free response. I think the free response questions you have to view on the computer, but I think you still write because like wolf trying to type out what your symbols and not a lot of fun, pretty time consuming. So again, just kind of like we'll talk more about that after I confirm that with the AP people. Miss Roshan, the name I'm trying to pull, does all the AP organization. Is everybody okay? Feel good? Okay. Marcelino, you need one of these sheets that adds back to everybody, and then when you get a minute, like ask one of your buddies to run through what you missed here in that first 10 minutes or whatever.
No problem.
Okay. All right. Ordinarily, I would do this on the smartboard, but for whatever reason, I can't seem to get it to attach to my tablet right now, so we're going to do it the old-fashioned way. Everybody's good? So this is a topic I would have liked. This would have been the last topic I would have liked to do in semester one, but we didn't get to it, and that's fine. It's a natural bridge between semester one and semester two. So whether we do it at the start of semester one or start of semester two or the end of semester one doesn't make a whole heap a lot of difference. So this is the last section in chapter 4. This is called antiderivatives. And we're going to start with the definition. So we say a function f is called an antiderivative of f on an interval I if the f prime of x is equal to f of x for all x in I. Now this sounds confusing, right? Here's the deal. A function's an antiderivative of f. If I take the derivative of that function, I get f back. So for example, if I have my function f of x is like 3x squared, the antiderivative is x cubed. Because what's the derivative of x cubed? 3x squared. That's all we're saying here. Does that feel okay? Now, one thing we have one little problem here. Does anybody see what the little problem is? Something should stick out right away as like, is x cubed the only antiderivative? No. Can you give me another one? How about x cubed plus 1? What's the derivative of x cubed plus 1? Still 3x squared, because what's the derivative of 1? 0, right? Oh, so who can give me another antiderivative of 3x cubed? X cubed plus 2. So how many antiderivatives are we going to be able to write? Infinitely many, right? So in general, what we'll do is we'll just say, okay, the antiderivative is really just x cubed plus some constant c, whatever that constant is, right? We call this the general antiderivative. Is everybody okay? Now, have I talked about how to find this antiderivative yet? No. And if you see what I did to get this, that's great. If you don't, that's okay. We're going to get into the nitty-gritty of like how I did this here in a moment. But if you're like, okay, that's fine, but like, how did you do that? If you're still asking that, that's okay, because we haven't explained it. It's not necessarily going to be obvious. Right now, what I want the takeaway to be is that if we think about this process of anti-differentiation as a function, one input has infinitely many outputs, right? Is that good or bad? That's bad, right? That's not a function, right? If we think about differentiation as a function, one input, exactly one output, that's good. The reverse process, though, one input has infinitely many outputs. Not a function anymore. It's just kind of a relation. That's the takeaway that we want right now. That's it. Is everybody okay? And the reason why we get infinitely many outputs is all you have to do is change the constant at the end, and you get a new distinct antiderivative. And that's all you have to do to change, or to get a new antiderivative, is just change the constant at the end. Yeah, it's good? Okay. So the general antiderivative is just some f of x plus c, exactly what we observed before, right? All right. So let's look at some specific examples, and we're going to write the general antiderivative for each, okay? Now, we haven't talked about exactly how to do this, but you guys all know how to do this, right? If you remember how to take the derivative, you know how to find the antiderivative, because all you're doing is using the same derivative rules in reverse. Okay? So our first example, our function is sine x. The antiderivative of sine x is going to be negative cosine x plus c, because the derivative, what derivative gives you sine? Well, the derivative, okay, so we remember that the derivative of, we don't have anything that gives us sine, but the derivative of cosine is negative sine, right? So if I just divide the negative sign over, right, the derivative of negative cosine is sine. And because it asks for the general antiderivative, we tack on a plus c. Oh, goodness. Yeah. Thank you. I love it when we're paying attention. Thank you. Yes. 100%. Negative cosine. Great googly moogly, Mr. Gulick. You're screwing up the first example here. It's not a great start. All right. Our next is we want the antiderivative for 1 over x. Well, what derivative gives us 1 over x? The derivative of natural log. So our antiderivative then should be the natural log of x plus c. Is everybody okay there? Our last one here, we have x to the n. Well, let's think about the reverse process. I take the derivative of what is going to give me x to the n.
And x 1 minus n, 2 1 minus n.
I'm going to need that, right? Because I need to multiply by the exponent. So if I multiply this by n plus 1, it needs to then divide by n plus 1, so my coefficient is 1, right? And take the derivative of a monomial, we subtract 1 from the exponent. So the exponent has to be n plus 1. Is everybody okay with that? So my antiderivative is just going to be x to the n plus 1 over n plus 1 plus c. Peyton.
Sorry, could you re-explain why you're dividing it by n plus 1?
So if I just take the derivative of this, I'm going to have n plus 1 times x to the n, right?
Yeah.
So this coefficient here needs to be 1. So if I just divide both sides by n plus 1, that'll make it what I need. Is that a better job of explaining it when I write it down a little bit more? Sorry, yes. Thank you for following up. If it's not clear, ask again. Be like, I'm not sure on that. Can you do it a different way or say it one more time? Happy to do those sorts of things, okay? What we're doing is not trivial, right? And if it's not obvious to you, it's not obvious to somebody else, and it's worth stopping and saying something, and we can do it again or do it a different way or talk some more about it or elaborate some more or give some more detail. I'm happy to do that. So far, so good? Okay. So in general, we have a table here. All this table is, we're just consolidating our derivative rules from first semester into reverse. Notice that there is one little difference here, and that it's the absolute value of x inside of our natural log. Why is there an absolute value there? What's the domain of the natural log? It's not all real numbers. It's positive, only positives. The natural log of 0 or a negative is undefined. Any logarithm of 0 or negative is undefined. That's why the absolute value is there. Because you can do like plug in -3 into 1 over x, but you can't plug -3 into the natural log of x. Okay. Now, in general, this process is much more difficult than taking a derivative, because there are functions where you can take the derivative of it rather easily, but there is no formula to do the antiderivative for it. But in practice, the vast majority of these problems, it's easier to do the antiderivative than it is to do the derivative. I can give you a derivative problem, make it as nasty as I want, and conceivably you can still do it. Like, you have all the tools you need to do it. Even if it has like 10 chain rules in it or something, like, sure. I can give you something that's like a simple product that's impossible to do as an antiderivative, and just the way it goes. We'll talk more about that in the future, elaborate on that idea. But in practice, this process is usually easier than the derivative. But in totality, it's much, much harder because there are things that are impossible to do this process on. Is everybody okay? Okay. Let's do another example. You're like, woof, Mr. Kulik, this is getting complicated. So the takeaway here, the first thing we want to establish, when we did derivatives of sums and differences, we could just do the derivative like piecemeal, right? We could just do the derivative of each sum or difference, each part of the sum or difference separately, right? Think we can do the same thing with the antiderivative? Yes. So I can just do the antiderivative of 4 sine x and the antiderivative of the other piece as 2 separate problems. When we took the derivative, what did I have to do with a constant in front of a function? I just ignored it, right? And it just came with us to the end, right? Like the derivative of 2x is just 2 times 1. Do you think I can do the same thing with the antiderivative? Yes. So those same derivative rules are going to apply where I can distribute it across the sum or difference, where I can pull the constant out front. All that still works the same way. So my recovered function g of x, what's the antiderivative of 4 sine x? Like 4 times negative cosine x, right? Or negative 4 cosine x would be fine. I'm just going to write it as like this way to start, because if you're going back and looking at your notes, I want it to be clear. And if you didn't catch this, we already answered that part of the question above, right? In a previous example, that's why I just asked it and somebody spit out the answer like so quickly and effortlessly, and you're like, how did you know that so fast? It's like, well, it's because we already did it. And I just remembered. So far, so good. What in the heck am I going to do with this stupid thing here? Oh, no. Simplify it first. Who said that? That's a great idea. How would I simplify that first? Wonderful. Wonderful choice. Why is that going to make life so much easier? Not if I divide it by x. That's okay. Yeah, these are questions that you should ask. If you don't see what we did, you should ask. Why is that better? Because I can just now use this formula, right? These are just x to the n's. Yes, Meredith. Well, we're going to just do 1 plus c for the whole thing. Does that make sense? So you can consolidate each of those plus c's together since they're all just constant. So c plus c plus c is just c again. Is that okay? But yes, great observation. Absolutely something we should talk about. That we just need 1 plus c for the whole anti-differentiation process, even if we did like 2 or 3 or 4 or 5 or 6 different separate antiderivatives. We're just going to use 1 plus c at the end because you can just consolidate a constant plus a constant plus a constant is still a constant. We're going to kind of abuse the notation a little bit and call that, still just call it c. Does that feel good? Okay. And now probably want to do a little tad bit of cleanup here. Is everybody okay with what I did? Again, just simplified the fractions and added stuff and distributed negatives and, like nothing fancy here. If you don't see it, holler at me, but it should be relatively straightforward, the simplification that happened there. Is everybody still doing all right? Notice that this process right now, essentially just the reverse of what we've been doing, right? And here's even the better part. You know how like when we do the derivatives, we have like chain product quotient rules? The actual going backwards from that is quite complicated, and we won't see that for quite some time. So for right now, it's just going to be the basic rules are all you're going to need to do this. All right, let's look at this next example. It says find f if f prime of x is equal to yada, 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 and f of 0 is equal to -2. What is this additional piece of information given? What is that going to do for us? That additional piece of information is going to allow us to find the specific c for this particular f. So rather than writing this as f of x equals yada, yada, yada plus c, because we know one point on that original function, we can find the specific c for that original function. So this process changes almost nothing other than it adds one extra step at the end where I have to find that c. Find the actual value for that c. Everything else remains the same, though. All right. So, again, we can do our antiderivatives one piece at a time. What's the antiderivative of e to the x? E to the x. I'm a little bit disappointed that all of you didn't yell that L at the same time, because that one should have been pretty easy. For the next one, obviously, we can probably pull that 20 out front. What's the antiderivative of 1 plus x squared to the -1? What if we wrote it instead as 1 over 1 plus x squared? Tan inverse. Who said it? I heard somebody say, yeah, well done. That's right. Is everybody okay? Remember how I told you that you had to have these things like memorized, like for real, forever memorized, because they're never going to go away? Even though we're not doing derivatives anymore, are we still using these same derivative rules? Yeah, they're never going to go away. Like you have to have these stone cold memorized, forward and backward now. Everybody's okay? All right, now let's solve for the c now. So if I know f of 0 is equal to -2, I can replace the f of x with -2. And all the x's with zeros. And then I can just solve for c. So far, so good. What is e to the 0? 1. What is tan inverse of 0? 0 is correct. Again, the way to think about that is the graph of tangent looks like this. So we have the coordinate 0, 0. So when y is 0, x is also 0. So tan inverse of 0 is 0. Okay, so what is c going to be then? -3. So that allows us to say then our function f of x is e to the x plus 20 tan inverse of x minus 3. Does that feel okay? So again, giving that extra point at the end, it's kind of like a big fat nothing burger, right? It just adds one little extra step, but it's usually like a pretty easy algebraic step, right? Now, do you have to remember like exponent rules or trig stuff? Yeah, possibly. Is that sometimes hard? Yeah, like remembering stuff is hard, but it's all stuff you should know, right? If you have to look it up, that's okay, but you should know what to do with it. You know what I'm saying? Let's look at the next one. It says find f if f double prime of x is equal to 12x squared plus 6x minus 4. And now we're given 2 points. Why are we given 2 points here instead of 1? Yes, very good. Because we're given a second derivative and asked to recover the original function. We're going to have to do that antiderivative process twice. Each time we do it, we generate a c. So we are going to need 2 separate points in order to do that. Is everybody okay? All right. So let's start. Let's find the first derivative. Let's recover that first. So what is the antiderivative of 12x squared? So we add 1 to the exponent and then divide by the new exponent. That's it. Is everybody okay? So when we do the derivative, we subtract and multiply. Here we add and divide, right? Not surprising if we're just going the reverse route. Yes? Okay. What's the antiderivative of 6x? Well, I shouldn't write it. I shouldn't go so fast. We add 1 to the exponent and divide by the new exponent. I'll write it that way. Going too fast, Mr. Kulik. It's the first day we're doing this. Settle down. I know. I just get excited, like. I know. It's exciting. Okay? And then, what's the antiderivative of -4? Excellent. -4x. And everybody can see that once Alice says it, right?
Oh, no.
You see it now, right? And we're also going to say plus, and I'm going to put a subscript on my c because I'm going to have 2 different c's in this. Is everybody okay? Can I use the points that I'm given yet? No, because what function have I just written? F prime. What are the points for? F, right? So I can't do anything with the points yet. I just do the process again. So let's simplify this. So that's going to be 4x cubed plus 3x squared minus 4x plus c1. Everybody's okay with a little bit of algebra or a little bit of arithmetic there real quick? Okay. Now let's go and take the antiderivative of this guy. So the antiderivative of 4x cubed is going to be 4x to the 3 plus 1 over 3 plus 1. Is everybody good? The antiderivative of 3x squared is going to be 3x to the 2 plus 1 over 2 plus 1. The antiderivative of 4x is going to be 4x to the 1 plus 1 over 1 plus 1. The antiderivative of c1 is going to be c1x, because c1 is a constant, right? The antiderivative of a constant is the constant times x, and then plus a second constant. If you want to call these like C and D, that's fine. You could do two separate letters. I like doing subscripts. Whatever your fancy is, that's fine. Let's simplify this down. Everybody's good? I have one equation with two unknowns, right? I have a C1 and a C2. Can I solve that directly? If I have two unknowns in one equation? No. What do I need to create? A system of two equations usually is what I need, right? Now, here they've given us convenient points that I don't actually need to make a system. What am I getting in here that makes this convenient? F of 0. Yeah, because what's going to happen when I plug 0 in for x? Everything but C2 is going to drop out, right? Or zeroing out. You guys see that? If it didn't, I'd have to create a system and solve a system. Now we don't have to do that in this situation. It's not quite as nasty as that. Is everybody, you see what I'm saying though, or no? Okay. So C2 is just going to be 4. You guys see why? And then I can say 1 is equal to 1 to the 4th plus 1 to the 3rd minus 2 times 1 squared plus C1 times 1 plus 4. So C1 there is -3. Oops, that's a 2. And I'll write as minus. Sorry. Do I need to move it up? I see people playing like head dodging in the back there. Again, if you need me to move stuff up, just holler if it's hard to see. How's this going so far? Does this feel pretty doable? Okay. All right, let's see what's next on our docket. Okay, so here it says we're given a function of f, and we want to make a rough sketch of its antiderivative such that f of 0 is equal to 2. This feels really hard, right? You look at this and you're like, I just don't not really computing what to do with this. Okay, so we don't give you anything else. Okay, so do I want to connect this now? What did they do here? I know what to do. I just want to check to see, like, it feels early to do what I would want to do here, and I want to look up and see if there's some other clever thing that they did instead. Okay. All right. So, yeah, that's fine. So let's say that this is our point 0, 2. Okay. So remember that this is the derivative, right? From 0 to 1, the derivative is negative. What should be happening to our function if the derivative is negative? It should be decreasing, right? So I don't know, there. From 0 to 1, it decreased. And then from 1 to 3, our derivative is positive, which means our function should be increasing. Everybody's okay there? And then from 3 on, our function is negative. Or sorry, our derivative is negative. So our function is decreasing. What do you notice, though, is going on here? Well, you're right on that, but I'm concerned about this minimum here that I see. What is that telling me? So the other thing that I'm going to worry about is the concavity of this function I've drawn, right? Probably should have thought about that in the first place, but I think I'm good so far. We'll go back and check. So if I think about this as this is going to be a change in concavity, right? As is this one. So like if I sketch in my second derivative, it's going to look like that or whatever. Because we're increasing here, so we're positive second derivative. We're decreasing there, so we're negative second derivative. And then we're increasing here, so positive second derivative. So concave up, concave down, concave up. So this should be like that, right? Because at 4, we're having that change in concavity. And really at 2, we're having that change in concavity. Is that okay with what we did there?
So anytime it's starting to if you have concavity, when you're doing the antiderivative, it is where the slope goes from.
So the concavity isn't. So we got to be careful with how we're explaining things, right? Because there's a lot of its and does because we're talking about 3 separate graphs, right? So I looked at the graph of the first derivative, the little f in this case, and I sketched out the graph of its derivative. That's the second derivative of cap f. So the places where the little f was increasing, its derivative would be above the x-axis. The places where little f is decreasing, the graph of its derivative should be below the x-axis. So I drew that, right? So I found there's two inflection points where concavity changes. The first one at 2 changes from concave up, so like a cup, to concave down, like a hill, like water runs off of it, which is what we're seeing here, right? Like I would catch water, and then here water would like run down. Everybody feel good? So that looks like that matches. Our second change in concavity happens at 4, where we go from concave down, like a hill, to concave up, which is what's happening, right? So that's the other piece that I wanted to make sure that I had. So we are decreasing, it's going down, but concave up. So because little f was negative, but its second derivative would be positive, we are decreasing and concave up, which is what I've drawn here, where the graph is still going down, but it's catching water as I go. Does that feel okay, David?
So you're using the second derivative to find the antiderivative?
So to draw the antiderivative, I'm going to use the first derivative to tell where the antiderivative is. Okay, let me be careful. To draw the antiderivative, I'm going to use little f to tell where the antiderivative is increasing and decreasing. And I'm going to use the derivative of little f to tell where the antiderivative is concave up and concave down.
Oh, okay.
Does that?
Yeah.
You have to be careful with the language here because we have derivatives and antiderivatives, and like the derivative of one thing is the like you just have to be careful in our explanation there. And I think I got a little sloppy there. So thank you for following up and letting me like be a little bit more careful with the explanation. I think everything I said before was correct. It was just like doing a better job of communicating what I was talking about. Does that, you're good though?
Yeah, that makes sense.
Okay. All right. Last couple of problems, example problems, and we're going to be done with this section. So here, these are story problems, and they should be familiar sounding story problems. So we say a particle moves in a straight line and has an acceleration given by a of t equals yada, yada, yada. Its initial velocity, v of 0, is -6, and its initial displacement, s of 0, is 9. Find its position function, s of t. So remember, what's the relationship between position, velocity, and acceleration? Is that the first derivative of position is velocity, and the first derivative of velocity is acceleration. But here we're asked to go this route, right? What are we going to be doing then? Antiderivatives. Does everybody feel good? Okay. So let's start by first writing the general antiderivative for velocity. So I'm going to start with my acceleration. What's the antiderivative of 6t?
6t 1 plus 1.
Good. Or you could say 6t squared over 2, or just write 3t squared. Any of those would be fine. Again, we're going to write it out like as thoroughly as possible here in the beginning, and then stop doing that after a section or two of doing this, because you guys are going to be like, yeah, I got it. And what's the antiderivative of 4? Well, t in this case, right? Because we have a of t. t is the name of our variable, so be careful with that. And then we also need a plus c. And now, let's go ahead and simplify this real quick. And now let's solve for the c. Why can I solve for c directly this time? Because the point that I'm given is for velocity. It's for the first derivative of position, right? It's like I'm given f and then f prime, a point on each of them. What is c going to be? Who can do it in their head without having to... Oh, yes, it should be 3t squared. Thank you. I did it too. It's just going to be -6, right? Because when you plug 0 in for t, everything drops off other than the c. Is that okay? Okay. Now let's do our general antiderivative of velocity. So what's our antiderivative of 3t squared? Yep, 3t to the third over 3. What's our antiderivative of 4t? Is everybody okay with what we did there? Let's simplify things down. All right, who can tell me what c is in their head without having to plug anything in? T is 0, right? 9. So when you see that you're given like that point at 0, that makes life so much easier. Oops. Plus 9. So there's our position function. Does that feel all right? Okay. Last example, and we'll be done for today. Sound good? All right. A ball is thrown upward with a speed of 48 feet per second from the edge of a cliff 432 feet above the ground. Find its height above the ground after t seconds. When does it reach its maximum height? When does it hit the ground? What is that first sentence telling us? A ball is thrown upward with a speed of 48 feet per second. Yeah. And the edge of the cliff is 432 feet above the ground. What is that piece telling us? Telling us S, well, let's do H, I guess, for height. H of 0 is 432.
Why is it 0?
Because that's at the start, right? A ball is thrown upward. Yes, 100%. Does that feel good?
Yeah.
Okay. So if I want to get a position function out of my velocity, what do I need? The antiderivative. So the antiderivative of 48 is just 48t plus c. What's that c going to be? Just 432, right? Oh my goodness, guys. Oh. Physics people, what's wrong? What didn't I count for? Gravity is yes, is the answer. Why? So there we go. So V of 0 is 48. H of 0 is 432. A of t is negative 9.8. Or if you're in physics, negative 10, but that just makes me cringe.
Negative 10?
Yeah.
Why?
Why round it? You're using a calculator anyways. It's one extra button to make it 9.8. You know? It's one extra dot. The difference between a 10 and a 9.8.
No, I mean, when you're writing it, I use my head.
All right, so I do the antiderivative to get to velocity. That constant has to be 48. Antiderivative of this and that constant has to be 432. Does everybody feel okay with what we did now? That looks a heck of a lot better to me. Okay. How do I find the maximum of a function? I'm going to do like a first derivative test. So I'm going to take v of t and set it equal to 0. So when I get that, I get t is equal to 48 divided by 9.8. Everybody's okay there? If I pick something less than that, if I pick like v of 1, what am I going to get? I'm going to get a positive, right? If I pick something bigger than that, like 6, what it's going to happen, I'm going to get a negative. That tells me that this is a maximum. Is everybody okay? And then it says, when does it hit the ground? Well, that I'm just going to solve h of t equal to 0. Is that okay? Just barely got that one in under the belt. The homework for 4.9 is here on the board. You should also, for next time, do the related rates problems. There's, what is there, 4 of them? These are the easiest version of these problems. Try to follow the directions and do the format that I suggest at the front. It'll make sense as we get deeper in and you see the more complex problems, because I'm trying to show you how the pictures and the labeling really make a difference as you get deeper in. It's hard to appreciate that early, but just trust me on it.
I'm going sad.
Okay, like you said, any majority of legal documents.